Power Integrated Circuit Switch. Welcome to this module on Power Integrated Circuit Switch products. This module will introduce the basics and the operational features of Power IC switches. It is 21 pages in length and will last just over 20 minutes. There are many different kinds of switches. In general, they can be thought of as either being mechanical or electronic. It would be fairly safe to say everyone has used a mechanical wall switch to turn lights on in their homes. The most common switches are symbolically shown here. In the electronic switch category, semiconductor devices are made up of NPN and PNP bipolar transistors, as well as N and P channel field effect transistors, or simply FETs. When a FET structure is used in an IC, it is more descriptively referred to as a metal oxide silicon field effect transistor, or more simply a MOSFET. MOSFET switch structures are used in very large numbers in ICs and bipolar transistors to a lesser extent. The mechanical electrical switch element shown here is the most common and most easily understood. Everyone is familiar with the inner workings of the mechanical switch element, and it is easily understood that switches connect or disconnect parts of a circuit to control currents. The purpose of a switch is to control electrical currents. An important trait of an efficient switch is that it exhibits an extremely high resistance to current flow when open or off, and be able to accommodate a large voltage across the switch without breaking down. When a switch is turned on, the switch will heat up. The heat is generated as a result of the current flowing through the inherent on resistance of the switch. Heating represents lost system energy and is sought to be minimized by making the switch on resistance as low as economically possible. When a switch is turned off, no current should flow. In practice, a very minute amount of current will flow around the switch as a result of leakage current paths having very high resistances. It again gives rise to heating and represents lost system energy. Good switches will exhibit many megohms of off resistance. An ideal switch is capable of switching an infinite amount of current, exhibit zero resistance to current flow when closed or on, and present infinite resistance when open or off, and be able to accommodate or stand off an infinite voltage. Ideal switches do not occur in real life, and for that reason are engineered to meet various parametric requirements. Some primary parameters of importance for practical switches are listed here. All of these parameters will be influenced by temperature, and the parametric temperature is always specified on datasheets. Low-side switch circuits derive their name from the fact that they all have their switching elements connected to ground or to the most negative voltage of the circuit, thus the name low-side switch. The load is always located between the positive power supply and the switch element and is always connected to the positive power supply. N-channel low-side switches are the most common since they can be operated from a single power supply and gate voltage needs only to be pulled up or positive for turn-on, much like the NPN transistor. P-channel low-side switches are not commonly used because it is somewhat more difficult to obtain a negative gate voltage for turn-on and requires more silicon area to accomplish the same on resistance, or RDS on, as an N-channel, and would as a result be more costly than an N-channel. High-side switch circuits derive their name from the fact that they have their switching elements connected to the positive power supply of the circuit, thus the name high-side switch. The load is always located between the switch and ground. Both P-channel and N-channel switches are used in high-side switch applications. When a P-channel high-side and an N-channel low-side power switch are configured as shown, the circuit can be referred to as a common drain half-bridge, since the drain terminals of both switches are tied together. More commonly, when the two switch elements require opposite polarities of input voltage for turn-on, the combination is said to be a complementary output switch. The advantage of the complementary output switch is that Control circuitry is simple when complementary power supplies are available. The Totem-Pole output is made up of two like elements used as high and low side switches. Operation is much the same as with the complementary output configuration, except for the control voltage polarities. Again, only one switch is allowed to be turned on at a time. For reference comparison to the complementary output, both positive and negative power supplies are retained. In this case, though, both switches require their gates to be pulled up relative to their individual source terminals for turn on. So as to not exceed the maximum gate-to-source voltage rating, two totally separate gate voltage sources must be incorporated. This makes the input control circuitry slightly more complex. Placing the motor between two N-channel totem-pole outputs, as shown here, creates an H-bridge circuit configuration. This configuration is frequently used in power IC switches designed to drive bidirectional DC motors. To further the scale of economy, the charge pump is frequently multiplexed or shared between the two high-side N-channel switches, since only one high-side switch is permitted to be on at any one time. An H-bridge circuit configuration can also be created by combining two half-bridge circuits using complementary output switch elements. The load would be placed between the two complementary half-bridge circuit outputs. IC switches not only provide load control, but also load protection and status or diagnostic communication. The various protection features are listed here. Dynamic clamping is accomplished by the placement of a blocking diode and Zener diode in series with each other and between the MOSFET's drain-to gate. The dynamic output clamp circuit protects power MOSFET outputs from avalanche breakdown caused when excessive voltages are present at the output. A frequently used approach to output current limiting is to add a second source 2 terminal, to the N-channel MOSFET switch. The output current limit protection circuit limits the switch's output current to safe operating levels. The power output switch is usually the only element of the IC that is thermally protected, since the power switch is normally the primary source of heat generation. Thermal shutdown is usually incorporated in a power switch along with current limit protection. This combination will allow the switch to continue to operate in an output current limiting mode so long as the thermal operating limit is not exceeded. In the overcurrent protection circuit, a shorted load causes the drain-to-source voltage, VDS, developed across the N-channel switch to rise significantly. A rise in the VDS voltage is monitored by an overcurrent detection circuit made up of a threshold reference comparator. V-thresh establishes the current turn-off threshold for the IC switch. If the VDS voltage attains V-thresh, the comparator output goes logic high, signaling the input control logic to turn off the MOSFET switch. Many IC switches incorporate schemes which provide multiple levels of output protection. The multiple levels include output current limiting, thermal shutdown protection, and overcurrent protection. An overvoltage shutdown circuit protects the power IC switch by monitoring the power supply voltage and shutting down the IC prior to the supply voltages ever reaching damaging levels. The overvoltage detection circuit usually involves a voltage reference comparator monitoring a voltage that is proportional to the voltage being sensed. ICs typically incorporate some means of protection against electrostatic discharge voltages, or ESD. All device terminals incorporate independent internal protection similar to that shown. Referring to the protection circuit on the right, ESD voltages presented to the device terminal break down the Zener diode. A breakdown of the Zener causes the transistor base voltage to rise, turning on the bipolar NPN transistor, dissipating the otherwise destructive energy to ground. Analog power ICs have many combinations of fault detection and fault reporting. Some devices detect faults and use the information internally to trigger protection systems, but do not output the fault. Most ICs do output fault information for diagnostic purposes. This information, when available to the user, is very valuable for troubleshooting purposes.